Thank you, Anne Marie, for organizing the committee, organizing the meeting and inviting me to give the presentation. I'm a researcher. I'm Zhang, a researcher from Center for the Built Environment, UC Berkeley. I saw my colleague Gail Brager. We are from the same group. And in my presentation, I will call CBE. A simple word. So if you heard CBE, that means the Center for the Built Environment, our group. And I'm a person, you know, the background is in the human area, how to, my background is more interested in the expertise is more in human physiology and thermal comfort. So that's why in my presentation, I will focus more on how people's comfort information can be sent into the HVAC control. So the HVAC air conditioning system control can react or respond to human comfort requirement. So that's the area I'm going to focus on. And it's also the expertise I have is in this area. And a little bit of background. We all know that we spent a lot of energy in buildings in order to create a thermal comfortable environment. However, it has been known quite consistently that occupants' satisfaction for the temperature is low. So that means the current way of using thermostat in the room is not working well, and we need a more effective control than the room thermostat. And what are the opportunities there? Mario already showed some of his study about using the IR image, infrared image. So the interesting thing is the IR image, IR camera is the cost and the sizes of the IR camera now has already significantly improved. The cost significantly reduced and the size is very small. So and also there are these personal comfort systems, which I will show you a couple of them in my presentation, that inherently already has a lot of IoT monitoring information and IoT features that send to the internet. Those information are available. So our goal is to how to take advantages of all those new developments and then assessing our thermal occupants' thermal comfort, make the HVAC control loop including thermal comfort information. So that's the goal, to make people comfortable with an energy efficient way. And in my presentation, I will basically has two parts. The first part is to describe how to make this closed loop control by inputting occupants' thermal comfort information. Second part focus on the opportunities for those personal comfort system, variable system, to make them available for the AI control of the HVAC. So the first project I'm going to describe is this is a funded project by DOE. It's using infrared sensor to improve comfort. There are three tasks in this project. The first one is to develop the sensing system. The second part is to using the sensing system information from the sensing system to assess occupants' thermal comfort. And then the third part is to send the occupants' thermal comfort information to the HVAC air conditioning control system to change the set point for the space. The project is led by Lawrence Berkeley National Laboratory and joined by CBE, DICAN, and Movitherm. This is the camera that our team, the entire team developed. It has two cameras, one IR camera and one color camera. And the color camera is used to help our IR camera to identify body parts like a cheek and hands. And then there's a pen tilt that will track in the occupants and a small computer board that's very small. The whole thing, including the single board computer, was about 4 inches, 10 centimeters, and the two cameras are each is about 2 or 3 millimeters. It's very tiny. So this is the opportunity of one of the opportunity with the development of the camera system for both IR camera and color camera. They are not only small and much lower cost. And what we did in our group discussion, we already heard some people mentioned this too. IR camera, you only record the data based on X and Y. It doesn't know where the body parts are from, where as a cheek temperature, where are the hand temperature. So we have to have this dual system, one IR camera, one visual camera. And we use the edge detection method. So both of them has edge detection and overlay them, the two images together. And color camera will know where is the cheeks, where are the cheeks and hand. Then we will, by this overlaying, we will get the temperatures from skin temperatures from those specific areas. So this is the flow, shows the flow, how this skin temperature was obtained by this dual camera system. And a little bit fundamental, I know some of you already know this, but for the broader audience, I need to explain a little bit more about fundamental. So our skin temperature, in fact, reflects our thermal comfort. In the cold environment, the skin will be, the blood will be constricted because the body trying to save energy. So you will end it with a larger skin temperature variation in the IR camera, skin temperature variation, which will be shown by the images taken by an IR camera. And when you are warm, because the body needs to release heat, they will try to vasodilate the vessels to pump all the blood to the superficial to release heat. So you will see a quite uniform skin temperature. That's the example of the two images I'm showing here. So for the warm environment, you see a more uniform environment. For the colder environment, you see more variation. And in our camera system, we will do we will capture not only the difference between different body parts, say the hands, the face, but we also within one part, like a cheek, or hands, we capture the temperature at a certain area. So that we will see the variation within even one area. That will help to identify people's comfort more accurately. And this slides I'm showing to see, to show how this skin temperature is linked to their perception as a thermal sensation. On the right-hand side, you can see the images that when people are cold, you can see a big variation between facial and hands, and the difference between within hand, the finger and the hand, you can see a large difference. So that means this person is cold. If you see the left-hand picture, you can see that hands, the Y shows the thermal sensation, X is different body parts. So hand and feet feels the coldest. And then the whole body thermal sensation, that was at the far left category, follows the hand and foot sensation, say also very cold. So this image shows the temperature linking to the volt. One very interesting thing is that whole body thermal sensation is very much dominated by the most discomfort local body sensation. They follows the foot and hand sensation. So that's very interesting. Tell us something. If we probably can significantly improve thermal comfort by focusing on those most discomfort body part, adding some heating to this local body part to heat them up. So this is what this perception figure tells us. And in the warmer environment, it's quite a different story. The head region, face, head, feel the warmest in the warmer environment compared with other body part. In the right hand side, you can also see the image. Again, it's quite a uniform distribution on the in the face and the hands. And then on the left hand side, you can see the whole body thermal sensation follows those head thermal sensation. Again, the warmest body part dictates the whole body thermal sensation. So that indicates something for efficient comfort. We should take care of the head thermal sensation, make it comfortable. And one might have questions, say, skin temperature, people and people are different. Let's say hands, some people naturally has warm hands, some people naturally have a cold hand. Then how do you identify there's comfort between the groups of populations? So this is the key. Is when you are cold, or even though the local's absolute temperature might be different, but the differences between the head and the hands, or difference between the hand itself, the trends are very similar between people. Same way for the warm condition. Although people and people are different, but the trends of the uniformity when they are warm quite similar among different populations. So that's a useful information we can use. Here I'm showing one example. By capturing the hand and forearm and finger skin temperature, we see the gradients correlate with the thermal sensation. X means thermal sensation, and Y is the temperature difference between finger and forearm. So you can see when they are colder, when the finger is lower than the forearm temperature, this temperature gradient is negative. Then the sensation is all on the cold side. On the neutral and the warm side, it's harder to distinguish between neutral and hot. So sometimes we need absolute temperature combined with the difference to predict comfort more accurately. So the previously all about explain some of the fundamentals, kind of like fundamentals, how skin temperature is linked with the thermal comfort, and how to capture skin temperature can predict or assess comfort. Then we can do a good way to to control the air conditioning more efficiently and ensure comfort. So second part of my presentation is about a personal comfort system, how to explore the opportunities from personal comfort systems. So what is a personal comfort system? It's occupants can control the heating and cooling from the local system for their own purpose. So those are called personal comfort system. You can change it, turn on, turn off, change the level of heating and cooling. And very often, those personal comfort system monitor many things. Here is a chair, heat and cooled chair built in our group. We have the heating and cooling. You can see the back for the, we have two control for the back and the seat area. Heating represented by the red light, cooling by the blue light, and the level of heating is all by the number of those light. So those informations are all stored in this IoT chair. It has the occupancy sensor, temperature, humidity sensor, and how user use it, heating, cooling, level of heating and cooling. And those information are all readily available to be used. So this is one opportunity. And those this slides show a couple images of the chairs. It doesn't have to be very intrusive. Something can be very built into chair very nicely. And in our chair design, we found the most sensitive body parts to heat and cool them. So that makes the chair very efficient. In our group discussion previously, we talk about the local heater. No, we don't want to encourage people use local heater because they use a tremendous big amount of energy. And those chair personal comfort system, we really emphasize efficiency. It's only about 7 watts on the seat maximum power, 7 watts on the back. So make it efficient is very important. And we did a study in a county office continued for 6 months. And we gave 40 chairs to 40 occupants monitored for 6 months. And the study results showed that people really like those personal comfort system, these chairs. 97% of people satisfied with the chair. That's almost never happened with the thermal comfort in field. It's very difficult to reach this level of comfort. And then 77% of the time when they are seated on the chair, they are using heating and cooling functions. So that's very encouraging. They are actively using them. And 20% of people, when they are using seating cooling, they're actually using back for heating. We ask why. They say that their lower back, their back hurt. So very often this warm back gave them comfortable sensation. So here I'm showing one of the example captured by this chair, this heat and cool chair. I explained it has all the sensors. So the gray bars in this chart shows the occupancy sensor. You can see the time when the occupants seated there. And then the red bars showing that they are using heating function of the chair. And the blue bars means that there are the time duration they are using cooling function, and the height of those bars representing the level of heating and cooling they are using, and the green light is the local ambient temperature. So through the 6 months study, we gathered such a large database that's ready to be used by we have a PhD thesis on this topic. If you are interested, can go to our website. So that's the opportunity. I'm giving one example that PCS, personal comfort system, can have those information for the AI control. And the second example that I'm going to give is this wearable device. My group, we did a study with a wearable wristband was manufactured by Amber Labs. This wristband has a heating and cooling function. We did the test in our lab. And when people are cool, they like to use a heating function. When people felt warm, they like to use a cooling function. And the chart in the middle, and because this variable also has this IoT feature, so all the information was obtained remotely, we can see that this is a particular test in the environment. You can see the percentage of people using cooling versus using heating. Cooling was the blue bars in this chart, middle chart. Red bars is the heating function. So from these bars, you can see, most people are cooled in this ambient temperature. So those information are very valuable from their usage, because in the US, very often buildings are overcooled. And overcooled building not only waste energy, it also doesn't provide hurt the people comfort. So that's why when we get this information, we really give us provide Maple opportunities. We can create a better environment for the comfort and then use less energy. However, now personal comfort system chairs variables are not that widely adopted. So that's an issue. As one of the challenge. How about the fans? So the fans, the CBE will have been studied for many years. Fans is widely used in buildings. They provide comfort in warm environment. The ambient temperature can easily set up several degrees C higher to achieving same comfort. And each degree set point increase, degree C set point increase corresponding to 50% of the energy, HVAC energy saving. So that's the opportunity. We can be more creative. In my lab, we are creating a base. In the base, we insert those capabilities sensor and occupancy sensor to help the control. And people's cooling head has a physiology reason. They like to cool the head because actually our body equipped with the sweating gland, the richest in the forehead. That's why a cooling head is more effective. And actually cooling head, this is my last slide, the cooling head preference across species. When your dogs run, you see their tongue coming out because they want to cool the veins by evaporate cooling. And the cools from the vein was transferred to the artery. So when the artery sent blood to the brain, it's already after the tongue, those evaporation already 2 or 3 degrees lower than the rest of the body. So this is a little bit additional information. Now I'm open for questions. Sorry, a little bit longer than I thought.
Well, thank you so much for the fascinating presentation. We appreciate that, and many of us work on the thermal comfort area, so it was a great presentation. So one question we have here is related to the link between thermal comfort and health and well-being. So have you looked at that link and how thermal discomfort affect health?
I myself, I have to say, I haven't done the study yet specifically on health, but I think it's that's always in my agenda. I was hoping I can do, because like the back chair, that's directly related with their back hurt. And also you saw the presentation when people cold, their hands and feet are vasoconstricted. At CBE, we developed foot warmer. So by dilating the area, we can really increase the blood circulation and make the warmer feet better. I think that also has a health benefit too. So this I haven't investigated yet. It's kind of in my agenda.
Thank you. Maybe this could be a collaboration opportunity among the people who are listening to you and who are interested in this area. So we encourage everybody to reach out to Hui if they're interested in that link. So another question we have here, Hui, for you is, how was the privacy of participants protected in these experiments? And the follow-up question, if these were all lab studies, and if you were to actually take these lab studies to the real offices or real environments, how would you consider, or how would you address privacy issues?
Privacy has been the issue, which I don't know how to solve. Right now, we are, in the field study, right now, the camera we are installing in one office, and we are planning install it in another office. It always has to have a visual camera for now, because IR camera, you know this a lot very well, cannot identify the locations. So for now, it's always the visual camera has been there. And then there's this privacy issue. And when we really running it, we can delete the visual camera information quickly. Once identified, then we delete the other issue. So we can just do by quickly deleting the images information. That's the current way. I don't have a better solution. Maybe other people can vision some of the other better choices.
Mm-hmm. Thank you so much. You have a lot of more questions that I couldn't ask in your speaker page because of time limitations. So I encourage you to go and add comments and maybe have an offline discussion there. They're really great questions. Again, thank you so much for the wonderful presentation.
Thank you.